Welcome to deep science sleep. Picture yourself nestled in a cozy cabin, wrapped in the softest blankets you've ever felt. Outside your window, gentle snowflakes drift down from a pearl gray sky, each one taking its own unhurried path to the earth below. The world has grown quiet in that special way that only winter can bring, as if nature itself has decided to speak in whispers. Your breath comes slow and easy, matching the peaceful rhythm of the falling snow. In this moment, there's nowhere you need to be, nothing you need to do. You're simply here, warm and safe, ready to drift through the most soothing facts about winter, each one like a gentle lullaby for your curious mind. Let the tensions of the day melt away like frost in morning sunlight. As we explore the quiet wonders of winter together, allow yourself to sink deeper into comfort, deeper into relaxation, deeper into the peaceful embrace of sleep, the magical architecture of snowflakes. There's something almost impossibly delicate about a snowflake landing on your mitten. Yet within that tiny crystal lies a story of remarkable complexity and beauty. Every snowflake that has ever fallen, every single one throughout all of history, began its journey in much the same way, yet arrived as something entirely unique. Understanding how these miniature ice sculptures form is like watching nature work as both scientist and artist, creating endless variations on a simple hexagonal theme. High in the atmosphere, where clouds gather and temperatures plummet well below freezing, water exists not as liquid but as vapor, invisible molecules floating through the cold air. For a snowflake to begin forming, this water vapor needs something to grab onto, a tiny nucleus around which it can start to build. This nucleus might be an almost invisibly small particle of dust that has drifted up from the Earth's surface. Could be a grain of pollen from flowers that bloomed months ago. Sometimes it's a microscopic piece of soot from a distant fire, or even a fragment of a volcanic particle that has traveled hundreds of miles on the wind. In the most pristine conditions, it might be sea salt that evaporated from ocean spray and found its way into the upper atmosphere. When the temperature drops to the freezing point, water vapor molecules begin to crystallize directly onto this tiny particle, bypassing the liquid phase entirely. This process, called deposition, is the birth of a snowflake. But it's not just any freezing that happens here. The water molecules, each consisting of 2 hydrogen atoms bonded to 1 oxygen atom, arrange themselves in a very specific way. The angle between the hydrogen and oxygen atoms is always 120 degrees, a fact determined by the fundamental physics of how these atoms bond together. When 3 of these molecules connect, they form a ring with 6 sides. This hexagonal structure is the foundation of every snowflake's shape, the underlying geometry that gives each crystal its characteristic 6-fold symmetry. As more water vapor freezes onto this initial hexagonal seed, the crystal begins to grow. But here's where the magic really happens. The crystal doesn't grow uniformly in all directions. Instead, it develops 6 arms extending from each corner of the hexagon. These arms, called dendrites, grow independently from one another, yet because they're all part of the same crystal and experiencing the same conditions at that micro level, they tend to develop similar patterns. It's this phenomenon that gives snowflakes their beautiful symmetry while also ensuring that each one is unique. The specific shape that a snowflake takes depends on the precise conditions it encounters as it grows and falls. Temperature plays a crucial role. When it's very cold, around -2 degrees Celsius, snowflakes tend to form as simple hexagonal plates, flat and relatively uncomplicated. As temperatures drop to around -5 degrees, the crystals develop into columns, like tiny pillars of ice. Between -10 and -15 degrees, the classic elaborate star shapes form, with their intricate branches and sub-branches creating patterns of stunning complexity. Drop the temperature even further, and the shapes simplify again into columns and plates. Humidity matters just as much as temperature. When there's more water vapor in the air, the snowflakes have more material to work with, and they tend to develop more elaborate structures. Those gorgeously complex snowflakes with multiple levels of branching typically form in conditions of high humidity. In drier air, the crystals remain simpler with less ornate patterns. It's remarkable to think that something as tiny as a snowflake can record, in its very structure, a detailed history of the atmospheric conditions it experienced during its formation and fall. As a snowflake falls through different layers of atmosphere, the conditions change continuously. It might start forming in one temperature zone, then fall into warmer or colder air, into regions of higher or lower humidity. Each change leaves its mark on the crystal structure. One branch might encounter a pocket of moisture and suddenly sprout side branches. Another part of the same snowflake might pass through drier air and develop more slowly. The journey from cloud to ground might take anywhere from 10 minutes to more than an hour, depending on the height of the cloud and the air currents the snowflake encounters. This is why no two snowflakes are truly identical. The number of variables involved is staggering. Consider that a typical snowflake contains about 10 quintillion water molecules. That's a 1 followed by 19 zeros. Each of these molecules arrives at the growing crystal at a slightly different time, in slightly different conditions. The likelihood of two snowflakes following exactly the same path through the atmosphere, encountering exactly the same sequence of temperatures and humidity levels, with molecules arriving in exactly the same pattern, is so vanishingly small that it's effectively impossible. Scientists have occasionally grown snowflakes in laboratory conditions, where they can control temperature and humidity with great precision. Under these controlled circumstances, they've been able to produce snowflakes that look identical to the naked eye. But even these laboratory twins, when examined at the molecular level, show differences. The arrangement of individual water molecules varies. It would be like two buildings constructed from the same blueprint, with the same number of bricks, but where each individual brick occupies a slightly different position. The study of snowflakes has a long and fascinating history. In the 1600s, the mathematician and astronomer Johannes Kepler wrote a small book pondering why snowflakes have 6 sides, attempting to understand the geometry behind their formation. But it was Wilson Bentley, a farmer from Vermont, who really opened the world's eyes to the incredible diversity of snowflake forms. Starting in 1885, Bentley developed a method for photographing individual snowflakes through a microscope. It was painstaking work. He had to work in the bitter cold, catching snowflakes on a blackened piece of wood, quickly transferring them to a microscope slide, and photographing them before they melted or sublimated away. Over his lifetime, he captured images of more than 5,000 snowflakes, and not one was identical to another. His photographs were beautiful, revealing to the world the stunning variety of forms that snowflakes could take. Bentley's work popularized the saying that no two snowflakes are alike, and modern science has confirmed his observation. Even with advanced microscopy and sophisticated imaging techniques, scientists have never found two snowflakes that were truly identical. Each one is a small miracle of physics and chemistry, a frozen moment that captures the unique atmospheric conditions of its birth and journey. The largest snowflakes on record were reportedly observed in Montana in January 1887, with witnesses claiming they were 15 inches across. While this measurement has never been verified with modern instruments, scientists do know that snowflakes can grow quite large under the right conditions. The largest confirmed snowflakes measured about 6 inches in diameter. These giant flakes tend to form when temperatures are near freezing and humidity is high, allowing multiple crystals to stick together into larger aggregates. As snowflakes accumulate on the ground, they don't remain pristine. The delicate branches break off. The crystals begin to change through a process called metamorphism, where the ice reorganizes itself in response to pressure and temperature. Fresh snow is light and fluffy because it contains a lot of airspace between the individual crystals. But over time, this snow compacts. The pointed edges of the snowflakes break off and the grains become more rounded. If the temperature fluctuates, causing slight melting and refreezing, the snow can form a crust. In high mountains and polar regions, where snow accumulates year after year, the weight of new snow compresses the old snow beneath it, gradually transforming it into glacial ice, a process that can take decades or even centuries. But in that moment when a snowflake first lands, before it's disturbed or begins to change, it represents something rather wonderful. It's evidence of the beautiful complexity that can arise from simple physical laws. The same forces that create a snowflake operate throughout the universe, building crystals and structures according to rules written in the language of atoms and molecules. Yet the specific form any given snowflake takes is unique to its individual journey, a one-time creation that will never be exactly duplicated. There's something deeply peaceful about that thought. Even in nature's most repetitive processes, there's room for infinite variety, for uniqueness, for surprise. Each snowfall is not just a blanket of white covering the earth, but a shower of millions of tiny, unique frozen sculptures, each one worthy of wonder. The silent slumber of winter hibernation. In the depths of winter, when the world grows cold and food becomes scarce, some animals perform a feat that seems almost magical. They shut down their bodies to a degree that appears impossible, slowing their metabolism so dramatically that they exist in a state between living and sleeping, neither fully asleep nor truly awake. This is hibernation, one of nature's most elegant survival strategies. And understanding how it works reveals just how remarkable living things can be in their adaptations to challenging conditions. True hibernation is more extreme than many people realize. When we think of hibernation, we often picture bears sleeping in caves. But bears aren't technically true hibernators. They experience what's called torpor, a lighter form of dormancy. True hibernators, like ground squirrels, woodchucks, and certain species of bats, undergo changes so profound that if you encountered one in its hibernating state, you might think it was dead. Consider the Arctic ground squirrel, which holds the record for the most extreme hibernation known in mammals. During the summer months, these small rodents are active and busy, feeding constantly to build up fat reserves that will sustain them through the winter. When autumn arrives and temperatures begin to drop, they retreat to their underground burrows, curl into tight balls, and begin the process of entering hibernation. Over the course of several hours, their bodies cool down. Their heart rate, which normally beats around 200 to 400 times per minute, drops to as few as 5 beats per minute. Their breathing slows from perhaps 50 breaths per minute to 1 breath every minute or even longer. But the most astonishing change is in body temperature. The Arctic ground squirrel's normal body temperature is around 37 degrees Celsius, similar to our own. During hibernation, however, it can drop to negative 2.9 degrees Celsius. Yes, below freezing. This makes the Arctic ground squirrel the only known mammal whose body temperature can drop below the freezing point of water and survive. How is this possible? The answer lies in a phenomenon called supercooling. The fluids in the squirrel's body don't actually freeze solid, even though they're below freezing temperature, because they're kept liquid through high concentrations of glucose and other compounds that act as biological antifreeze. The purpose of lowering body temperature so dramatically is to conserve energy. When an animal's body is warm, it burns energy quickly. All the chemical reactions that keep us alive, collectively called metabolism, proceed at rates determined largely by temperature. Cool things down and those reactions slow down. By allowing their body temperature to drop, hibernators reduce their metabolic rate to a tiny fraction of its normal level. An Arctic ground squirrel in deep hibernation uses only about 1 to 2% of the energy it would use when active. This means those fat reserves built up during summer can last through the entire winter, even though the animal isn't eating at all. But hibernation isn't a continuous state of suspended animation. Even true hibernators need to warm up periodically. For the Arctic ground squirrel, these arousal periods happen every 2 to 3 weeks. The animal's metabolism kicks back into gear, generating heat rapidly through a process called thermogenesis. Special fat deposits, known as brown adipose tissue or brown fat, are particularly good at producing heat. Within a few hours, the squirrel warms back up to normal body temperature. These warming periods are energetically expensive, using up much of the squirrel's stored energy. During these brief warm periods, the animal doesn't eat or drink. Instead, it mostly sleeps. This seems paradoxical at first. Why would an animal that's been in a state of dormancy for weeks need to wake up to sleep? The answer relates to the fact that hibernation and sleep are fundamentally different states. Sleep is necessary for brain maintenance. During sleep, the brain consolidates memories, clears out metabolic waste products, and performs various maintenance tasks. But these processes require the brain to be at a certain temperature. During deep hibernation, when the brain has cooled to near freezing, it can't perform these necessary functions. So hibernators must periodically warm up to achieve normal sleep and allow their brains to perform essential maintenance. After 12 to 24 hours of normal body temperature, during which the animal spends much of its time in genuine sleep, it cools back down and returns to hibernation. Woodchucks, also known as groundhogs, are another example of true hibernators, though they don't supercool like Arctic ground squirrels. During hibernation, a woodchuck's heart rate drops from about 80 beats per minute to just 5 beats per minute. Its body temperature falls from around 37 degrees Celsius to just a few degrees above freezing. A hibernating woodchuck takes only about one breath every 6 minutes. In this state, the animal is deeply unconscious. You could handle it and it wouldn't wake up. The woodchuck remains in this hibernation state for up to 150 days, emerging in early spring when its internal clock, which continues ticking even in hibernation, signals that winter should be ending. The question of how hibernators know when to enter and exit hibernation has fascinated scientists for centuries. The triggers are complex, involving multiple factors. Day length plays a role. As days grow shorter in autumn, this change is detected by the animal's eyes and processed by a part of the brain called the pineal gland, which produces hormones that prepare the body for hibernation. Temperature is another factor. As the environment cools, this triggers physiological responses. But perhaps most remarkable is that hibernators have an internal calendar, a circannual rhythm similar to our circadian rhythm but operating on a yearly rather than daily cycle. Arctic ground squirrels, for instance, have been kept in laboratories under constant conditions with no seasonal cues, and they still enter and exit hibernation on schedule, following an internal program that tells them when winter should be happening. Bears, though not true hibernators, still undergo remarkable changes during their winter torpor. A black bear's heart rate drops from about 40 to 50 beats per minute to as low as 8 beats per minute. Unlike true hibernators, bears don't drop their body temperature dramatically. It might decrease by only 5 to 10 degrees Celsius. This means they're not as deeply unconscious as true hibernators. A bear in its winter den can be roused relatively easily, and if conditions aren't quite right, it might emerge from the den temporarily before returning. But bears have their own remarkable adaptations. They don't eat, drink, urinate, or defecate for months. In humans or most other mammals, not urinating for even a few days would lead to dangerous buildup of toxic waste products in the blood. Bears avoid this problem through an elegant biochemical trick. They recycle the waste products. Urea, the main waste product from protein breakdown that's normally excreted in urine, is instead broken down and its nitrogen used to build new proteins. Water that would normally be lost in urine is retained. The bears essentially exist in a perfectly closed system, living off their stored fat while maintaining their muscle mass and organ function. Female bears face an even more impressive challenge because they give birth during hibernation. A pregnant bear enters her den in late autumn. In January or February, while still in her winter torpor, she gives birth to tiny, helpless cubs. The cubs are extraordinarily small for the size of the mother, weighing only about 1 pound each. They're born blind and nearly hairless. But even in her dormant state, the mother bear can nurse them, producing milk rich in fat and calories. The cubs grow rapidly, nursing constantly, and by the time the mother emerges from the den in spring, they're much larger and ready to follow her into the world. Bats represent another fascinating group of hibernators. Many species of bats in temperate regions hibernate in caves or mines where the temperature remains stable and just above freezing. A little brown bat's heart rate can drop from over 300 beats per minute to fewer than 10. Its breathing might occur as infrequently as once every 90 minutes. The bat's body temperature drops to within a degree or two of the ambient temperature. Hanging upside down from the cave ceiling, these bats look like small, furry icicles. They can remain in this state for months, only occasionally waking to change position or to drink water if it's available. The evolution of hibernation has enabled these animals to survive in places that would otherwise be impossible for them. Without the ability to hibernate, small mammals couldn't survive winters in the Arctic or high mountains. They would either starve as food became unavailable or freeze as temperatures plummeted. But by lowering their energy demands to near zero, they can wait out the harshest months of the year, emerging when spring returns and the world becomes hospitable again. There's something deeply calming about the thought of hibernators resting in their burrows and caves, sealed away from the cold world above. While winter storms rage and temperatures plummet, they lie curled in darkness, their breathing so slow and quiet that you might not notice it, their hearts beating only a few times per minute, utterly still and at peace. They're not struggling against the winter or fighting to survive. Instead, they found a way to simply bypass the difficult season, to pause their lives until conditions improve. It's a complete surrender to the season, a profound letting go that allows nature to run its course while the animal waits, patient and still, for the world to awaken again. The celestial dance of the aurora borealis. There are few sights in nature quite as mesmerizing as the aurora borealis, those mysterious curtains of light that shimmer and dance across the night sky in polar regions. To witness the northern lights is to see something that seems almost impossible, as if the sky itself has come alive with color and movement. Yet for all their ethereal beauty, the auroras are the visible manifestation of fundamental physics, the product of interactions between the sun, the Earth's magnetic field, and the gases in our atmosphere. Understanding how this celestial display comes to be makes it even more wonderful. The story of an aurora begins not on Earth, but on the sun, 93 million miles away. The sun is not a solid object, but rather a ball of superhot plasma, electrically charged particles so energized that electrons have been stripped away from their atoms. This plasma is in constant, roiling motion, driven by powerful magnetic fields and by the tremendous heat generated by nuclear fusion in the sun's core. The visible surface we see, called the photosphere, is actually the coolest part of the sun's outer layers, with a temperature around 5,500 degrees Celsius. But above this lies the sun's atmosphere, and here things get even hotter and more violent. The outermost part of the sun's atmosphere, called the corona, reaches temperatures of over 1 million degrees. At these extreme temperatures, the particles are moving so fast that the sun's gravity can't hold them. They stream away from the sun in all directions, creating what we call the solar wind. This isn't wind in the sense of moving air. It's a constant stream of charged particles, mostly electrons and protons, flowing outward through the solar system at speeds of several hundred kilometers per second. When this solar wind reaches Earth, which takes about 2 to 3 days, it encounters our planet's magnetic field. Earth acts like a giant magnet with magnetic field lines extending far out into space. This magnetic field, called the magnetosphere, normally deflects most of the solar wind around the planet, protecting us from this radiation. The interaction creates a teardrop shape, with the side facing the sun compressed and the side away from the sun stretched out into a long tail. But the protection isn't perfect. Some of the charged particles from the solar wind manage to sneak through, particularly near Earth's magnetic poles. Here's where the geometry becomes crucial. Earth's magnetic field lines converge at the poles, funneling charged particles down into the upper atmosphere. It's similar to how water swirls down a drain, with the particles following the invisible highways created by magnetic field lines. These particles enter Earth's atmosphere at altitudes between about 100 and 400 kilometers above the surface. At these heights, the atmosphere is very thin but not absent. It contains atoms and molecules of oxygen and nitrogen, the same gases that make up most of the air we breathe at ground level. When the energetic particles from space collide with these atmospheric gases, they transfer their energy to the gas atoms. This energy excites the atoms, bumping their electrons into higher energy states. But electrons don't like to stay in these excited states. Within a fraction of a second, they fall back down to their normal energy levels, and when they do, they release the extra energy as light. This is the light we see as an aurora. The color of the light depends on which gas is involved and how much energy was transferred. Each element produces its own signature colors, like a fingerprint made of light. Green is the most common aurora color, and it comes from oxygen atoms at altitudes between about 100 and 200 kilometers. When oxygen is excited at these heights, it produces a brilliant yellow-green light. This is the color you'll see in most aurora photographs, those luminous green curtains that seem to flow like water across the sky. Pure red auroras are less common but spectacular when they occur. These also come from oxygen, but from oxygen at higher altitudes, above 200 kilometers. At these heights, the atmosphere is so thin that oxygen atoms can remain in an excited state for much longer before releasing their energy. When they finally do emit light, it glows deep red. Nitrogen produces blue and purple hues. Lower altitude nitrogen, below about 100 kilometers, can create a reddish-purple glow at the very bottom edge of an aurora display. Higher up, nitrogen glows blue. Sometimes you'll see auroras that appear pink or white. These are usually combinations of red and blue from nitrogen, or mixes of oxygen and nitrogen light blending together. The aurora isn't static. It moves and changes because the flow of charged particles from the sun is constantly varying. The solar wind isn't smooth and steady, but rather turbulent and gusty. When a particularly energetic stream of particles arrives, the aurora brightens and becomes more active. The curtains of light can pulse, ripple, and swirl, sometimes moving across the sky with remarkable speed. This dancing quality is one of the aurora's most captivating features. You can watch for hours and never see the same pattern twice. The intensity and frequency of auroras are closely linked to the sun's activity level, which follows an approximately 11-year cycle. During solar maximum, when the sun is most active, it produces more and stronger eruptions. These are called solar flares and coronal mass ejections. A coronal mass ejection can hurl billions of tons of plasma into space at speeds of several million kilometers per hour. When one of these massive eruptions happens to be directed toward Earth, the result can be a particularly strong geomagnetic storm, producing auroras that are visible much farther from the poles than usual. During these major storms, the northern lights have been seen as far south as the Caribbean, and the southern lights have been visible from Australia. The most powerful geomagnetic storm ever recorded occurred in September 1859, known as the Carrington event after the astronomer who observed the solar flare that caused it. The resulting auroras were so bright that people could read newspapers by their light at midnight. The lights were visible as far south as Cuba and Hawaii. Telegraph systems around the world went haywire, with some operators receiving electric shocks and papers catching fire from the induced currents. Though auroras are most commonly seen near the poles, they actually form in oval rings centered roughly on the magnetic poles rather than the geographic poles. These auroral ovals expand and contract with solar activity. During quiet periods, the ovals are small and situated at high latitudes. When a geomagnetic storm strikes, the ovals expand toward the equator, bringing auroras to lower latitudes where they're rarely seen. The best places to see auroras are within what's called the auroral zone, a ring roughly centered on each magnetic pole at about 65 to 70 degrees latitude. In the northern hemisphere, this includes northern Alaska, northern Canada, Iceland, Norway, Sweden, Finland, and northern Russia. In the southern hemisphere, the auroral zone mostly overlies Antarctica and the surrounding ocean, making it less accessible, though southern Australia, New Zealand, and the southern tip of South America occasionally see displays. The aurora australis, or southern lights, is essentially identical to the aurora borealis. The same processes create both, and they often occur simultaneously, like mirror images on opposite sides of the planet. The reason the northern lights are better known is simply because more people live within viewing range of them. The southern auroral oval mostly passes over ocean and uninhabited Antarctica, while the northern oval passes over populated regions. Ancient peoples around the world observed auroras and created myths to explain them. The Inuit peoples of Alaska called them spiritual lights and believed they were the spirits of their ancestors playing a ball game with a walrus skull. Some groups thought they were dangerous and that whistling at them would cause them to descend and harm you. The Norse believed the auroras were reflections from the shields of Valkyries as they led fallen warriors to Valhalla. Native American tribes had various interpretations, with some seeing them as dancing spirits and others as lights from fires in the far north. Scientific understanding of auroras developed slowly. In the 1600s, the French philosopher Pierre Gassendi coined the term aurora borealis, combining aurora, the name of the Roman goddess of dawn, with boreas, the Greek word for north wind. But it wasn't until the late 1800s that Christian Birkeland, a Norwegian physicist, proposed that auroras were caused by electrons from the sun being guided to the poles by Earth's magnetic field. He couldn't prove his theory at the time, but later observations confirmed he was essentially correct. Astronauts aboard the International Space Station have a unique view of auroras. The station orbits at about 400 kilometers altitude, which places it right at the top of the auroral zone. From this vantage point, the astronauts can see auroras at eye level or even slightly below them, watching as the glowing curtains extend downward toward Earth's surface. Photos taken from the station show the aurora as a bright band of green or red stretching around the planet's curve, with stars visible in the black sky above and city lights twinkling on the dark Earth below. Earth isn't the only planet with auroras. Any planet with both an atmosphere and a magnetic field can produce them. Jupiter has incredibly powerful auroras at both poles, created by its enormous magnetic field interacting with particles from the solar wind as well as from its volcanic moon Io. Saturn's auroras have been observed to pulse in time with its rotation. Even Mars, which has only a weak, localized magnetic field, shows diffuse auroral glows in regions where its crust is strongly magnetized. There's something deeply soothing about watching an aurora. Unlike most astronomical events that happen on timescales too slow or too fast for us to perceive in real time, the aurora moves at a pace we can watch and appreciate. The curtains sway and pulse with a rhythm that seems almost alive, neither too fast to follow nor too slow to maintain interest. Colors blend and shift. Rays of light shoot upward from the horizon, then fade away. New curtains form while old ones dissipate. The whole sky can become a stage for this silent, luminous performance. And it is silent. Despite occasional reports of sounds associated with auroras, they're essentially soundless. The aurora is happening far too high in the atmosphere to produce sounds that could reach the ground. Any noises you might hear are likely from other sources. The aurora itself is a visual phenomenon, light without sound, a cosmic whisper that speaks only to the eyes. Earth's gentle tilt and the winter solstice. The reason we have winter at all, the reason the world cools and days grow short, comes down to something surprisingly simple. Earth doesn't sit up straight. Our planet is tilted on its axis, leaning like a top that started to wobble. This tilt, just 23.5 degrees away from perpendicular to our orbit around the Sun, is responsible for the changing seasons that mark the rhythm of life on Earth. And once each year in the Northern Hemisphere, usually on December 21st or 22nd, this tilt creates a moment of particular significance. The winter solstice, the shortest day and longest night of the year. To understand the solstice, we need to picture Earth's journey around the Sun. Our planet traces an elliptical path, taking 1 year to complete each orbit. But contrary to what many people think, the changing seasons aren't caused by Earth getting closer to or farther from the Sun. In fact, Earth is actually closest to the Sun in early January, during Northern Hemisphere winter, not summer. The seasons are entirely about that tilt. Earth's axis of rotation, the imaginary line running from North Pole to South Pole, doesn't point straight up and down relative to its orbit. Instead, it's tilted at that 23.5-degree angle, and crucially, the direction of this tilt stays essentially constant as Earth moves around the Sun. Imagine Earth as a spinning top leaning to one side. As it circles the Sun, sometimes the Northern Hemisphere leans toward the Sun and sometimes it leans away. When the Northern Hemisphere leans toward the Sun, it receives more direct sunlight and experiences longer days. This is summer. 6 months later, when Earth is on the opposite side of its orbit, the Northern Hemisphere leans away from the Sun. The sunlight arrives at a steeper angle, spreading the same amount of energy over a larger area and providing less warmth. The days are shorter. This is winter. The Southern Hemisphere, of course, experiences the opposite seasons at the same time. The winter solstice is the moment when the Northern Hemisphere is tilted as far away from the Sun as it's going to get all year. At this instant, the Sun is positioned directly over the Tropic of Capricorn, an imaginary line circling Earth at 23.5 degrees south latitude. For anyone in the Northern Hemisphere, the Sun appears at its lowest point in the sky at noon. It rises at its most southerly point on the eastern horizon and sets at its most southerly point on the western horizon. Because the Sun's path across the sky is so low and the Sun stays above the horizon for such a short time, this is the day with the least sunlight all year. The exact timing of the solstice varies slightly from year to year, occurring at a specific moment rather than lasting all day. This moment, when the sun reaches its most southerly position, can happen at any time during December 21st or 22nd, depending on the year and your time zone. In 2024, for instance, the Northern Hemisphere winter solstice occurred on December 21st at 4:21 a.m. Universal Time. How much daylight you receive on the solstice depends on your latitude. At the equator, day length barely changes throughout the year, with the solstice bringing only a few minutes less daylight than any other day. But as you move north, the effect becomes more pronounced. In New York City, at about 40 degrees north latitude, the winter solstice brings roughly 9 hours and 15 minutes of daylight. In London, at 51 degrees north, there are only about 7 hours and 50 minutes between sunrise and sunset. In Reykjavik, Iceland, at 64 degrees north, daylight lasts just over 4 hours. Above the Arctic Circle, which sits at 66.5 degrees north latitude, something remarkable happens on the winter solstice. The sun doesn't rise at all. This circle marks the southernmost latitude where the sun can remain below the horizon for a full 24 hours. On the solstice itself, places right at the Arctic Circle experience a day where the sun just barely fails to peak above the horizon at what would be noon. Farther north, the period of darkness extends. At the North Pole, the sun set in late September and won't rise again until late March. The winter solstice sits right in the middle of this long polar night, a period of continuous darkness that lasts for months. Yet even in this darkness, there's not utter blackness. During the polar night, there's still civil twilight for several hours around midday. The sun, though below the horizon, is close enough that its light illuminates the atmosphere, creating a deep blue glow. As the weeks pass and the sun sinks farther below the horizon, this twilight period shrinks until, in the depths of winter, true darkness reigns for 24 hours. But the solstice marks the turning point. From this moment forward, the sun begins its slow return. Each day after the solstice, it climbs a tiny bit higher. The periods of twilight lengthen. Eventually, months later, the sun will finally break the horizon again, and the long polar day will begin. The winter solstice has held profound significance for human cultures throughout history. Many ancient monuments were built with the solstice in mind, their architecture aligned to capture sunlight in specific ways on this particular day. Newgrange, a Stone Age monument in Ireland built around 3200 BCE, predates Stonehenge and the Egyptian pyramids. It features a passage that aligns perfectly with the rising sun on the winter solstice morning. For just about 17 minutes, as the sun rises, light streams through the passage and illuminates the central chamber, something that happens only on this one day of the year. The builders of Newgrange, working with stone tools and without written language, nonetheless possessed sophisticated astronomical knowledge and constructed a monument that has perfectly captured the solstice sunrise for over 5,000 years. Stonehenge in England, built in stages between approximately 3000 and 2000 BCE, aligns with both the summer and winter solstices. While it's better known for its summer solstice alignment, when the sun rises over the heel stone, the winter solstice was likely equally important to its builders. On this day, The sun sets between the two largest stone trilithons, creating a dramatic frame for the dying light of the year's shortest day. Many cultures celebrated festivals around the winter solstice, marking it as a time of renewal and the promise of the sun's return. The Roman festival of Saturnalia, held in late December, was a time of feasting, gift-giving, and the temporary reversal of social norms. The Persian festival of Yalda celebrated the longest night of the year with gatherings where people would stay awake until dawn, sharing fruits and stories. The East Asian tradition of Dongji, meaning extreme of winter, marked the solstice as a time when yang energy began to increase, bringing warmth back to the world. The placement of Christmas on December 25th, just a few days after the solstice, likely reflects the influence of these older solstice celebrations. As Christianity spread through the Roman Empire and beyond, it absorbed and adapted existing seasonal festivals. The symbolism of light returning to the world fit naturally with Christian themes of hope and renewal. Today, many winter holidays, whether religious or secular, carry echoes of that ancient recognition of the solstice as a turning point, a moment when darkness reaches its peak and then begins to recede. After the solstice, the return of light is gradual, almost imperceptible at first. In the days immediately following the shortest day, the change is measured in seconds. But those seconds accumulate. By early January, the difference becomes noticeable. By February, the days are noticeably longer than they were in December. The sun rises earlier and sets later. It climbs higher in the sky at noon, its rays arriving at a less steep angle, warming the earth more effectively. This gradual lengthening of days triggers responses in living things. Plants, though they may be dormant and snow-covered, sense the changing light through photoreceptors. As day length increases, it signals that spring is approaching, though still months away. Birds respond to increasing daylight by beginning to sing more frequently. Their endocrine systems, triggered by the lengthening days, start preparing them for the breeding season ahead. Even in the depths of January and February, when winter often feels most severe, the biological world is beginning to stir, responding to the same astronomical signals that humans have marked and celebrated for millennia. There's a comforting rhythm to the solstice and the seasonal cycle it represents. No matter how long the nights grow, no matter how cold the weather becomes, the solstice assures us that this is as far as it goes. The next day will have a little more light. The day after that, a little more still. The universe operates according to reliable, predictable patterns. Earth continues its steady orbit, its axis tilted at its constant angle, and the seasons follow their appointed rounds. There's something deeply reassuring in this certainty, a reminder that even the darkest night gives way to dawn, and the coldest winter eventually yields to spring. The quiet freeze of lakes and ice formation. Water is one of the most familiar substances on Earth, yet it behaves in ways that are genuinely unusual, even strange, when compared to most other materials. These peculiar properties become especially apparent in winter, when water transforms into ice. The way lakes freeze, the structure of ice itself, and the implications of these processes for life in frozen waters all reveal the remarkable nature of this simple molecule that covers most of our planet. Most substances contract as they cool. The molecules move more slowly, get closer together, and the material becomes denser. Water does this too, but only up to a point. As liquid water cools from room temperature, it contracts and becomes denser, just as you'd expect. But something strange happens when it reaches 4 degrees Celsius. At this temperature, water reaches its maximum density. Cool it any further, and it actually begins to expand and become less dense. This is highly unusual behavior, and it happens because of water's molecular structure and the way water molecules interact with each other. A water molecule consists of one oxygen atom bonded to 2 hydrogen atoms, arranged in a bent shape rather than a straight line. The oxygen atom has a slight negative charge, while the hydrogen atoms have slight positive charges. This makes water a polar molecule with a positive end and a negative end. These opposite charges attract, so the positive end of one water molecule is drawn to the negative end of another. These attractions, called hydrogen bonds, are weaker than the covalent bonds that hold the atoms within each molecule together, but they're strong enough to significantly affect how water behaves. In liquid water, molecules are constantly moving, making and breaking hydrogen bonds with their neighbors. As water cools below 4 degrees Celsius, the molecules slow down enough that the hydrogen bonds can hold them in a more organized arrangement. This arrangement is less compact than the random jumble of molecules in liquid water. The molecules position themselves in a specific geometry, creating open spaces in the structure. This is why ice is less dense than cold water. If you've ever wondered why ice floats, this is the answer. The solid form is actually less dense than the liquid form, which is the opposite of how most substances behave. This seemingly small detail has enormous implications. Because ice is less dense than water, it floats. This means that lakes, ponds, and even oceans freeze from the top down rather than from the bottom up. When winter arrives and air temperatures drop below freezing, the surface of a lake begins to cool. The cold water at the surface, being denser than the warmer water below, sinks. This creates a circulation pattern called turnover, where water from the depths rises to replace the sinking surface water. This continues until the entire water body reaches 4 degrees Celsius. Once the whole lake is at 4 degrees, further cooling of the surface creates water that's less dense. This lighter, colder water stays at the surface rather than sinking. When the surface water reaches 0 degrees Celsius, it begins to freeze. Ice crystals form, starting perhaps around a tiny particle of dust or a bit of organic matter that acts as a nucleus for crystallization. The ice crystals grow, spreading across the surface. Under calm conditions, clear ice can form, with water molecules arranging themselves into a beautiful crystalline lattice. Each water molecule in ice is hydrogen bonded to 4 neighbors in a tetrahedral arrangement, creating a hexagonal crystal structure similar to what we see in snowflakes. The initial ice is often thin and transparent. You can sometimes see through it to the water below, observing fish swimming beneath this ceiling of ice. As the ice thickens, it becomes stronger. On a small pond, an inch or 2 of ice might form in a single night of hard freezing. On larger lakes, the ice grows more slowly, but it can eventually reach thicknesses of a foot, 2 feet, even several feet in regions with harsh, prolonged winters. Not all ice is the same, though. Clear ice, also called black ice because you can see the dark water through it, forms when water freezes slowly under calm conditions. This ice is strong and homogeneous. But ice can also form when snow falls on the frozen surface and becomes waterlogged, then freezes. This creates white ice, which is weaker than clear ice of the same thickness because it contains air bubbles and has a less uniform structure. Experienced ice fishers and winter travelers know to test the ice and distinguish between these types, because their strength differs significantly. As ice grows thicker, it insulates the water below from the cold air above. Ice is actually a reasonably good insulator. A layer of ice slows the transfer of heat from the water to the air, which means the rate of ice growth decreases as the ice gets thicker. The first few inches form quickly, but subsequent growth happens more and more slowly. On a very large, deep lake, the ice might never reach the bottom no matter how cold the winter, because the thick layer of ice insulates the deeper water from freezing temperatures. This insulation effect is crucial for aquatic life. If lakes froze solid from bottom to top, most aquatic organisms would die. Fish, frogs, turtles, and countless invertebrates survive winter beneath the ice, living in the cold but liquid water below. The water at the bottom of a frozen lake remains at around 4 degrees Celsius, the temperature of maximum density. This is cold, certainly, but it's above freezing. Many fish become less active in this cold water, their metabolism slowing down, but they don't freeze. Some fish, like carp and bullheads, can survive with remarkably low oxygen levels. Important because oxygen doesn't dissolve as well in cold water and can't be replenished from the air when the surface is frozen. Turtles have an even more remarkable strategy. Some species of turtles can survive for months under ice by essentially shutting down. They don't breathe through their lungs during this time. Instead, they absorb tiny amounts of oxygen directly through their skin and the lining of their mouth and cloaca. Their metabolism drops to a fraction of its normal rate. They don't eat, hardly move, and wait in a state of suspended animation for spring to arrive. Frogs have evolved various strategies. Some species, like bullfrogs, burrow into the mud at the bottom of ponds where it's slightly warmer and oxygen is available. Others, including wood frogs, actually allow themselves to freeze solid. About 70% of the water in a frozen wood frog's body turns to ice. His heart stops beating. Its breathing ceases. By most measures, it appears to be dead. But the frog survives because of antifreeze compounds in its cells, particularly glucose at very high concentrations. These compounds prevent ice crystals from forming inside cells, which would rupture the cell membranes and cause death. The ice forms only in the spaces between cells. When spring arrives and temperatures rise, the frog thaws, its heart begins beating again, and it resumes its life as if waking from a very deep sleep. Even plants living at the bottom of frozen lakes continue their lives, albeit slowly. Aquatic plants photosynthesize if enough light penetrates the ice. Clear ice allows substantial light through, supporting this underwater ecosystem. Algae and other microorganisms remain active, though their growth rates are much reduced in the cold. The ice itself undergoes changes as winter progresses. Temperature fluctuations can cause the ice to expand and contract, creating pressure ridges and cracks. When ice expands rapidly, usually during a sharp cold snap, it can produce loud booming and cracking sounds that echo across the frozen landscape. These sounds can be startling if you're not expecting them, like gunshots or thunder rolling across the ice. But they're simply the ice adjusting to temperature stress, similar to how buildings creak and settle. Sometimes, when snow falls on clear ice while the ice is still relatively thin, it creates beautiful patterns. The weight of the snow can slightly depress the ice, allowing water to seep up through cracks and flood the snow. When this freezes, it creates a layer of white ice on top of the clear ice below. If snow falls again and the process repeats, you can end up with alternating layers of clear and white ice, creating a striped appearance when viewed from the side. In the Arctic and Antarctic, ice formation occurs on a much grander scale. Sea ice forms when ocean water freezes. Because ocean water contains salt, it has a lower freezing point than fresh water, around -1.8 degrees Celsius. When sea ice forms, much of the salt is excluded from the crystal structure, concentrating the salt in the remaining liquid water and making it even denser and more likely to sink. This process, called brine rejection, is one of the driving forces behind ocean circulation. The dense, salty water sinks and flows along the ocean bottom, forming deep ocean currents that circulate throughout the world's oceans. Multi-year sea ice in the Arctic can grow to several meters thick. Ice sheets and glaciers, formed from compacted snow on land, can be thousands of meters thick. The Greenland ice sheet reaches depths over 3,000 meters. The Antarctic ice sheet is even more massive, averaging about 2,000 meters thick and reaching maximum depths over 4,700 meters. These ice masses contain about 68% of the world's fresh water. If all the ice on Earth melted, sea levels would rise by approximately 70 meters, enough to submerge most coastal cities. But let's return to our peaceful frozen lake on a quiet winter evening. The ice is solid, perhaps a foot thick, enough to walk on safely. Snow covers the surface, muffling all sound. The world is hushed. Beneath the ice, in the dark water, life continues its slow winter rhythm. Fish hover near the bottom, barely moving. Turtles rest in the mud. The whole system waits patiently for the return of warmth. There's something profoundly peaceful about the frozen lake. It represents a complete transformation. The same water that rippled and splashed in summer, now solid and still. Yet this transformation is temporary, a pause rather than an ending. Spring will come, temperatures will rise, and the ice will melt. But for now, in the depths of winter, the frozen lake rests under its blanket of ice and snow, quiet and beautiful, a testament to the remarkable properties of water and the elegant ways life has found to survive even in the coldest conditions. The great winter journeys of migrating birds. Each autumn, billions of birds embark on journeys that seem almost impossible. Small songbirds weighing less than an ounce fly thousands of miles across oceans and deserts. Waterfowl navigate from the Arctic tundra to southern wetlands. Raptors soar on thermals across continents. These migrations represent some of the most impressive feats of endurance and navigation in the animal kingdom, and understanding how birds accomplish these journeys reveals the remarkable capabilities evolution has granted them. Migration happens because resources, particularly food, are not evenly distributed across the planet throughout the year. In summer, high northern latitudes explode with life. The long days and warm temperatures create ideal conditions for insects, which emerge in enormous numbers. Plants grow rapidly, producing seeds and berries. Wetlands teem with fish and amphibians. For birds raising young, this abundance provides plenty of food for hungry chicks. But this bounty is temporary. As autumn arrives and temperatures drop, insects die or enter dormancy, plants stop producing seeds and berries, and water begins to freeze. Birds that stayed would face starvation. Rather than endure these harsh conditions, many bird species migrate to warmer regions where food remains available through winter. This strategy has evolved independently in many bird lineages and exists on every continent except Antarctica. The distances traveled vary enormously. Some species migrate only a few hundred miles, moving from higher elevations to lower ones or from inland to the coast. Others undertake journeys spanning half the planet. The Arctic tern holds the record for the longest migration of any animal. These slender seabirds breed in the Arctic during the northern summer, then fly to the Antarctic for the southern summer, effectively experiencing summer year-round. One Arctic tern, tracked by researchers, flew over 96,000 kilometers in a single year. That's more than twice the circumference of the Earth. Over its lifetime, which can span 3 decades, an Arctic tern may fly the equivalent of 3 round trips to the moon. How do birds know when to migrate? The triggers are complex and involve multiple factors. Day length is crucial. As days grow shorter in autumn, this change is detected by birds' eyes and processed by their brains, triggering hormonal changes. These hormones prepare the bird for migration, causing it to eat more and build up fat reserves. A small songbird might nearly double its body weight before migration, with much of the added weight being fat that will fuel the long flight ahead. Temperature also plays a role, though it's generally less important than day length. A sudden cold snap might trigger migration in some species, while unseasonably warm weather might delay it. Food availability matters too. Some birds don't begin migrating until their preferred food source starts to decline. Swallows, which feed on flying insects, often linger until insect populations crash with the first hard frosts. But there's also an internal component. Birds raised in captivity with no exposure to seasonal changes still show migratory restlessness, called Zugenruch in German, at the appropriate times of year. They become agitated, fluttering and hopping in their cages, oriented in the direction they would normally migrate. This restlessness is programmed genetically, an internal calendar that tells the bird when it's time to move even without environmental cues. Once a bird begins its migration, it faces the challenge of navigation. How does a bird that hatched just a few months ago, with no prior experience, find its way from Alaska to South America? The answer is that birds use multiple navigation systems, combining information from various sources to find their way. Many birds use the sun as a compass. The sun's position in the sky changes predictably throughout the day, moving from east to west. But using the sun for navigation isn't as simple as just flying toward it or away from it. The bird needs to account for the sun's movement, essentially knowing what time of day it is and adjusting its orientation accordingly. Birds have an internal clock that allows them to make this correction. Even when raised in captivity with no view of the sky, birds can orient correctly using the sun when they're finally released, suggesting this ability is at least partly instinctive. At night, many migrants use the stars. The night sky rotates around the celestial poles, and the star patterns near these poles move least over the course of the night. Young birds appear to learn the pattern of stars around the celestial pole and use this as a reference point. Experiments with planetariums have shown that if you raise birds under an artificial sky that rotates around a different point, they'll use that false celestial pole for navigation, showing that this is at least partly learned behavior. But perhaps most remarkably, birds can detect Earth's magnetic field and use it as a compass. The Earth acts as a giant magnet, with field lines running between the magnetic poles. Birds can sense both the direction of these field lines and their angle relative to Earth's surface. Near the equator, field lines run horizontally. At the poles, they run vertically. In between, they're at angles that vary with latitude. By sensing this angle, a bird can determine not just which direction is north, but also how far north or south it is. The mechanism by which birds sense magnetic fields is still being researched, but it appears to involve special proteins in their eyes called cryptochromes. These proteins undergo chemical reactions when exposed to blue light, and these reactions are influenced by the Earth's magnetic field. Essentially, birds may be able to see the magnetic field as a pattern superimposed on their visual field. Disrupting cryptochromes with bright light can interfere with birds' magnetic compass. Supporting this theory, birds probably don't rely on just one of these navigation systems. Instead, they use them together, cross-checking information from different sources. If the sun is visible, they might rely primarily on it. On overcast days, they might switch to using the magnetic field. At night, they might use the stars. This redundancy makes their navigation robust, allowing them to stay on course even when conditions make one system unreliable. Many birds migrate in flocks, and the V-formation that geese and ducks use isn't just for show. It's an energy-saving strategy. Each bird except the leader flies slightly above and to the side of the bird in front of it, positioning its wingtip in the updraft created by the bird ahead. This reduces the energy cost of flight significantly. The birds take turns leading, with the lead bird dropping back when it gets tired and another bird taking its place at the front. Small songbirds often migrate at night, which might seem counterintuitive. But night migration has several advantages. The air is generally calmer at night, with fewer thermals and less turbulent wind. Temperatures are cooler, reducing the risk of overheating during the strenuous flight. Night flight also allows birds to spend daylight hours foraging to rebuild their energy reserves. And flying at night may reduce predation risk from hawks and other daytime hunters. These nocturnal migrants face special challenges. They can't feed while flying in darkness, so they must carefully manage their energy reserves. A small warbler might fly for 8 to 10 hours straight, covering several hundred miles in a single night. When dawn arrives, it must find suitable habitat to rest and refuel. If it's crossing the Gulf of Mexico, a common route for birds migrating from the eastern United States to Central and South America, there's no place to stop. The bird must have enough energy reserves to make the entire crossing, which can take 18 to 20 hours of continuous flight. Not all birds make it. Migration is dangerous. Birds face bad weather, predators, exhaustion, and disorientation. Storms can blow them off course or force them down over open water. Bright lights from cities can disorient them, causing them to circle in confusion until they're exhausted. Windows kill hundreds of millions of birds each year when migrants crash into reflective glass. But despite these dangers, the majority of birds complete their migration successfully, an achievement that speaks to the power of evolved behavior and the drive to survive. Young birds making their first migration face particular challenges. In some species, the adults leave first, abandoning their offspring before they're ready to migrate. The young birds must find their way to the wintering grounds on their own, following genetic programming and innate navigation abilities. Despite having no experienced birds to follow, most of them make it. In other species, families migrate together, with young birds learning the route from their parents. Whooping cranes, for example, migrate in family groups, and young cranes learn the migration route by following their parents. If whooping cranes raised in captivity are to be reintroduced to the wild, they must be taught the migration route. In an innovative conservation program, biologists have led captive-raised cranes on their first migration using ultralight aircraft, literally showing the birds the way south. Once the cranes have made the journey following the plane, they remember the route and can complete future migrations on their own. As winter progresses and day length begins to increase after the solstice, some birds start preparing for the return journey. Spring migration often happens faster than fall migration. Birds are rushing to return to their breeding grounds to secure the best territories before competitors arrive. The urge to migrate north is so strong that birds sometimes arrive at their breeding grounds before winter has fully released its grip, gambling that food will become available soon enough for them to survive. There's something awe-inspiring about bird migration, this twice-yearly movement of billions of individuals across the planet. On any given night during migration season, hundreds of millions of birds are aloft over North America alone, flying through the darkness toward distant destinations. Most of us never see them. We wake to find new species in our yards, birds that weren't there yesterday, pausing briefly in their journeys before continuing on. Or we notice that familiar summer residents have vanished, departed for warmer climes we'll never visit. The fact that a tiny warbler weighing half an ounce can fly from Canada to Venezuela and back each year, finding its way across thousands of miles without maps or GPS, navigating by sun and stars and magnetic fields, is genuinely remarkable. These journeys, repeated year after year for millions of years, connect distant ecosystems and make migration one of the planet's great natural phenomena. And it all happens driven by the simple need to follow the seasons, to be where food is available to survive and reproduce. The pageant of migration is one of winter's hidden wonders, happening largely unseen as birds move through the darkness, heading toward warmth while we sleep peacefully below. Trees' winter dreams and dormancy. When winter arrives and trees stand bare against gray skies, they might appear lifeless, dead, waiting for spring's magic to resurrect them. But trees aren't dead in winter. They're dormant, in a state of suspended animation that's as carefully orchestrated and complex as any of their other seasonal behaviors. Understanding how trees prepare for and survive winter reveals the sophisticated strategies plants have evolved to endure months of freezing temperatures and reduced light. Trees sense the changing seasons through multiple environmental cues, but day length is the most reliable signal. Temperature can fluctuate unpredictably. An early cold snap might arrive while days are still relatively long, or warm weather might persist well into autumn. But day length follows an absolutely predictable schedule, determined by Earth's position in its orbit. As summer passes and the autumnal equinox approaches, days grow progressively shorter, and trees respond to this change. The detection system involves photoreceptors, proteins sensitive to light, particularly red and far-red wavelengths. The ratio of these wavelengths changes as day length changes, and this shift triggers chemical cascades within the tree's cells. These signals travel through the tree, preparing it for dormancy. One of the key chemicals involved is abscisic acid, a plant hormone that promotes dormancy and inhibits growth. As days shorten, abscisic acid levels increase throughout the tree. For deciduous trees, those that drop their leaves in autumn, the first visible preparation for winter is the magnificent display of fall color. This display isn't just trees dying, but rather trees actively recovering valuable nutrients before discarding their leaves. All summer, leaves have been the tree's food factories, using chlorophyll to capture sunlight and convert carbon dioxide and water into sugars through photosynthesis. But leaves are expensive to maintain in winter. They'd lose water through evaporation that the tree can't replace when the ground is frozen. They'd be vulnerable to damage from ice and snow. And in the low-light conditions of winter, particularly at high latitudes, they couldn't photosynthesize enough to justify their cost. So deciduous trees prepare to jettison their leaves, but first they salvage what they can. Chlorophyll, which makes leaves green, contains nitrogen, a valuable nutrient that's often in short supply. The tree breaks down the chlorophyll molecules and transports the nitrogen back into its branches and trunk for storage. With the green chlorophyll gone, other pigments that were always present in the leaf become visible. Carotenoids produce yellow and orange colors. Anthocyanins, which the tree produces in response to bright light and cold temperatures acting on sugars trapped in the leaf, create red and purple hues. The brilliant colors we associate with autumn are essentially the tree's other pigments being revealed as chlorophyll disappears, combined with new pigments produced as a side effect of the nutrient recovery process. At the base of each leaf stem, where it attaches to the twig, the tree creates an abscission layer, a special zone of cells that will break down and separate. As this layer weakens, the leaf's connection to the tree becomes fragile. Eventually, the leaf's own weight or a gust of wind is enough to make it fall. The tree seals the wound left behind with a layer of cork cells, protecting the exposed tissue from infection and water loss. Meanwhile, buds for next year's leaves and flowers have already formed. If you examine a bare winter twig closely, you'll see these buds, small and tightly sealed. Inside each bud are miniature leaves or flowers, already formed but arrested in development, waiting for spring. The buds are protected by specialized scales, thick and often waxy or resinous, providing insulation and waterproofing. Some buds, like those of horse chestnuts, are covered in a sticky resin that helps protect them from both cold and hungry animals. Evergreen trees, those that keep their leaves through winter, face different challenges. Their leaves, usually needles or small, waxy-coated leaves, are adapted to survive freezing temperatures. Needles have several advantages over broad leaves. Their small surface area reduces water loss. Their thick, waxy coating provides additional protection against evaporation and helps prevent ice crystals from forming inside the leaf tissue. The narrow shape sheds snow easily, preventing branches from being weighed down and broken. But even evergreens enter a form of dormancy in winter. They stop growing. Photosynthesis continues, but at a much reduced rate. The tree is essentially idling, maintaining itself but not trying to grow or reproduce. This conservation of energy is crucial for surviving winter. All trees, whether deciduous or evergreen, must protect their tissues from freezing damage. Water inside cells poses a particular problem. When water freezes, it expands and forms ice crystals that can puncture cell membranes, killing the cell. Trees have evolved several strategies to prevent this. One approach is to allow water to freeze, but only in controlled ways. Water in the spaces between cells can freeze without causing damage, but water inside cells must remain liquid. Trees accomplish this through supercooling and the production of antifreeze compounds. As temperatures drop, trees increase the concentration of sugars and other dissolved substances in their cells. These solutes lower the freezing point of water, similar to how salt on roads prevents ice from forming. Some trees produce specialized proteins that bind to tiny ice crystals and prevent them from growing larger. These antifreeze proteins allow the liquid water inside cells to cool below the normal freezing point without turning to ice. Different tree species have different cold tolerances, reflecting their evolutionary history and the climates where they evolved. Tropical trees, not adapted to freezing, can die when temperatures drop just a few degrees below freezing. Temperate trees can typically survive temperatures well below 0 Celsius. Boreal trees, those that grow in the far north, can withstand temperatures below -40 degrees Celsius or even colder. The record for cold tolerance may belong to the Dahurian larch, which grows in Siberia and can survive temperatures below -60 degrees Celsius. This cold hardiness isn't constant throughout the year. Trees gradually acclimate to cold as autumn progresses, becoming more and more freeze-tolerant. If a severe frost comes too early in autumn, before trees have fully prepared, it can cause significant damage. Similarly, if trees break dormancy too early in spring and then freezing temperatures return, the tender new growth can be killed. The timing of dormancy entry and exit is crucial, and trees have evolved to respond to reliable seasonal signals rather than short-term temperature fluctuations. While the above-ground parts of trees are dormant in winter, the roots continue some activity. Root growth can continue as long as the soil temperature remains above freezing, even when the air temperature is well below 0. The soil acts as insulation, buffering the roots from the most extreme air temperatures. Snow cover provides additional insulation. A blanket of snow traps air, which is a poor conductor of heat, creating a layer that protects the soil from bitter cold. Under deep snow, soil temperatures might remain just below freezing even when air temperatures are -30 degrees or colder. The roots take advantage of this relatively warmer soil to continue growing slowly throughout winter. They absorb water and nutrients when soil conditions allow. This winter root growth helps trees prepare for the burst of growth that will come in spring. When the buds break and leaves begin to expand, they'll need water immediately. Having an already extensive root system ready to supply that water gives the tree a head start. Trees also face the challenge of desiccation in winter. Even though they're not actively growing, they still lose water through their bark and, for evergreens, through their needles. But when the ground is frozen, they can't replace that lost water. This is why trees, particularly evergreens, can sometimes die during winter, not from cold but from drought. The technical term is winter burn or desiccation. It's especially common on the south and west sides of trees, where winter sun can warm the bark and needles, increasing water loss while the frozen ground prevents water uptake. To minimize water loss, deciduous trees seal off the wounds where leaves detached. Evergreens have their waxy needle coatings. Both types of trees can also close their stomata, the tiny pores on leaves and needles through which gas exchange occurs. By keeping stomata closed, trees reduce water loss, though this also limits their ability to photosynthesize since they need to take in carbon dioxide through these same pores. Some trees in harsh climates have evolved remarkable adaptations. Willows in the Arctic can survive completely frozen for months. When spring arrives and they thaw, they resume growth as if nothing unusual had happened. The ability to survive freezing solid is rare in woody plants, but these Arctic willows have mastered it, joining animals like wood frogs in their ability to freeze and thaw without injury. As winter progresses towards spring, trees remain dormant even as day length increases. They've entered deep dormancy, a state where they won't resume growth even if conditions become favorable. This prevents them from being fooled by temporary warm spells. A week of mild weather in January could trigger growth if trees responded simply to temperature, but then returning cold would damage the tender new growth. Deep dormancy requires not just warm temperatures but also a period of cold. Trees essentially need to experience winter before they'll allow spring to begin. This is measured in what are called chilling hours, the accumulated time spent at cold but not freezing temperatures. Only after trees have experienced sufficient cold do they become ready to respond to warmth and longer days. This is why spring arrives as a gradual awakening rather than a sudden switch. First, the sap begins to flow. Sugar maples famously produce sweet sap in late winter, which can be collected and boiled down into maple syrup. The sap flows when freezing nights are followed by warm days, creating pressure differences that push the sap up from the roots. Then buds begin to swell as the miniature leaves and flowers inside them start to grow. The bud scales separate slightly. Eventually, they burst open and fresh green leaves emerge, impossibly delicate and vivid after months of brown and gray. Flowers bloom, often before leaves appear fully, taking advantage of the sunlight that reaches through bare branches. But all of this is still weeks or months away on a winter evening. For now, the trees stand patient in their dormancy. Their metabolism is at a minimum. Growth has ceased. They're waiting, conserving energy, protected by their bark and their antifreeze compounds and their deep dormancy. They've shed what they couldn't maintain through winter. They've prepared buds for the next growing season. They've sent their roots into the soil to continue the slow work of gathering resources. There's something profoundly restful about dormant trees. They embody patience, the ability to wait without anxiety for the right moment to act. They don't struggle against winter or wish it were spring. They've adapted to the season so completely that dormancy isn't hardship but strategy. In their stillness, they demonstrate perfect acceptance of the present moment, neither rushing ahead to what comes next nor clinging to what has passed. When you look at a winter forest, at the gray-brown trunks and bare branches against a pale sky, you're seeing trees in their winter dreams, dormant but alive, waiting but not inactive, preparing for spring even as they rest in winter's grip. And in their patient waiting, there's a lesson worth contemplating as you drift towards sleep. Sometimes the wisest response to harsh conditions isn't to fight but to rest, to conserve energy, to trust that difficult seasons pass and that the time for growth will come again. The serene physics of winter stillness. Winter has a quality that other seasons lack, a particular kind of stillness and clarity that makes it distinctive. The air feels different on your skin in winter, not just colder but somehow cleaner, sharper. Sounds carry differently, colors change. The very physics of the world shifts in subtle but perceptible ways that create winter's unique atmosphere and character. The cold air of winter holds less moisture than warm summer air, and this difference affects nearly everything. Air's ability to hold water vapor depends on temperature. Warm air can contain a lot of moisture, which is why summer often feels humid and sticky. Cold air has much lower capacity. The same amount of water vapor that might create moderate humidity in summer produces saturated, foggy conditions in winter. When winter air is cold enough, there's simply very little water vapor present at all. This dryness contributes to winter's clarity. Water vapor in the atmosphere scatters light, creating haze and reducing visibility. With less water vapor present, winter skies can be remarkably clear. On a cold winter night far from city lights, the stars appear brighter and more numerous than at other times of year. The Milky Way stretches across the sky like a river of light. You can see individual stars that would be invisible in summer's hazier conditions. The low humidity also affects how cold feels. Dry cold is easier to tolerate than humid cold. This might seem counterintuitive since we often talk about how dry cold is more dangerous, but there's truth to both statements. At moderately cold temperatures, dry air feels less uncomfortable than moist air because it doesn't conduct heat away from your body as efficiently. Moisture is a good conductor of heat. Humid air in contact with your warm skin steals heat rapidly, making the same temperature feel colder when it's humid than when it's dry. But at very cold temperatures, the dryness becomes a hazard. Breathing extremely dry, cold air can damage lung tissue. The air must be warmed and humidified before reaching the lungs, a job your nasal passages and throat normally handle. But there's a limit to how much warming and humidifying they can do. At extreme cold, breathing becomes difficult and potentially harmful. This is why people in the coldest climates sometimes wear masks or scarves over their faces, pre-warming and pre-humidifying the air before they breathe it. The dryness also affects everyday objects. Wood shrinks in winter as it loses moisture to the dry air. This is why wooden doors and drawers that fit perfectly in summer might stick in winter, then loosen up when humidity returns in spring and the wood swells again. Musical instruments made of wood require careful humidification in winter to prevent cracking. Antique furniture sometimes shows splits and cracks that formed during dry winters past. Your skin responds to winter's dryness too. With less moisture in the air, water evaporates from your skin more readily, leaving it dry and sometimes cracked. Lips chap, hands become rough. These are the prices we pay for living in an environment where water exists mainly as ice rather than vapor. Snow, when it falls, transforms the acoustic environment in remarkable ways. Fresh, fluffy snow is filled with air pockets between the individual ice crystals. These air pockets absorb sound waves, damping their propagation. After a fresh snowfall, the world becomes quieter. Sounds that normally carry long distances fade away quickly. Your footsteps are muffled. Voices don't carry as far. Even the ambient noise of modern life, the distant hum of traffic and machinery, diminishes. This sound-absorbing quality of snow creates an almost eerie silence. In a forest after fresh snowfall, you can experience a level of quiet that's rare in the modern world. Stand still and listen, and you might hear almost nothing. No wind because the air is calm. No birds because many have migrated and others are silent in winter. No insects because they're dormant or dead. No rustling of leaves because deciduous trees are bare and evergreen needles are too stiff to rustle much. Just profound, deep silence broken only by the occasional creak of a branch or the soft sound of snow sliding from a tree. This silence isn't complete absence of sound, though. There are winter sounds, delicate and subtle. Snow falling makes almost no sound, but if you listen carefully, you can sometimes hear a whisper as flakes land on other flakes. Ice forming on a pond makes quiet popping and creaking noises. Frost forming on plants can produce tiny, almost inaudible clicking sounds as water crystallizes. These sounds are so quiet that in any other season they'd be drowned out, but in winter's silence, they become audible. Frost itself is one of winter's most beautiful phenomena. When the temperature drops below freezing and there's some moisture in the air, frost can form on any surface that's cold enough. Frost formation is similar to dew formation, but instead of water condensing as liquid droplets, it crystallizes directly from water vapor into ice. The resulting ice crystals can take many forms depending on conditions. Hoar frost forms when water vapor deposits directly onto surfaces, creating delicate, feathery crystals that grow perpendicular to the surface. On cold, calm nights with high humidity, hoarfrost can coat every surface with a layer of crystalline ice, transforming ordinary objects into fantastic frost sculptures. Bare branches become outlined in white. Grass blades turn into clusters of tiny ice needles. The whole world can appear to be decorated with intricate white lace. Window frost, less common now that most windows are double-paned and better insulated, forms when moisture inside a building condenses on cold glass and freezes. The ice crystals grow in elaborate patterns, forming fern-like shapes called frost flowers. Each window frost pattern is unique, determined by tiny imperfections in the glass, variations in temperature and humidity, and air currents near the window. People used to wake on winter mornings to find their windows decorated with these natural artworks, opaque with frost until the morning sun melted them away. Rime ice forms when supercooled water droplets in fog freeze onto surfaces. Unlike hoar frost, which grows from water vapor, rime ice builds up from actual liquid water that's below freezing but hasn't frozen yet. When these supercooled droplets touch a surface, they freeze instantly, building up layers of ice on the windward side of objects. In mountains and high elevations where freezing fog is common, rime ice can accumulate to remarkable thicknesses, coating trees and rocks in ice several inches thick and transforming forests into alien landscapes of white. Winter light has qualities that differ from other seasons. The sun stays low in the sky even at noon, producing longer shadows and softer, more angled light. In summer, midday sunlight comes from nearly overhead, creating short, dark shadows and harsh, bright illumination. In winter, sunlight arrives at a more shallow angle all day long, producing the kind of warm, directional light that photographers prize. Shadows stretch long even in the middle of the day. The light has a golden quality, particularly in late afternoon. As the low sun's rays pass through more atmosphere, scattering blue wavelengths and allowing reds and oranges to dominate. This low-angle light reveals textures that harsher summer light flattens. Snow-covered landscapes become studies in subtle shading, with every gentle undulation visible as a pattern of light and shadow. The bark of trees shows every ridge and groove. Frost crystals catch the light and sparkle like scattered diamonds. The night sky in winter offers its own rewards. The ecliptic, the path the sun follows across the sky, is tilted differently relative to the horizon in winter. This brings different constellations into view. Orion, perhaps the sky's most recognizable constellation, is primarily a winter sight in the northern hemisphere. The brilliant star Sirius, the brightest star in the night sky, shines in the winter constellation Canis Major. The Pleiades star cluster, a small group of bright stars huddled together, is best seen in winter evenings. The combination of long nights, clear skies, and dry air makes winter ideal for stargazing. The moon, when it's full, shines brilliantly in the cold, clear air, bright enough to cast distinct shadows on snow. These moon shadows, sharper and more defined than moon shadows in other seasons, add to winter's magical quality. But perhaps the most serene aspect of winter is simply its slowness. In summer, everything happens quickly. Plants grow visibly from one day to the next. Insects buzz and fly. Animals are active. The world rushes with life. Winter operates at a different pace. Changes happen slowly, almost imperceptibly. Snow accumulates gradually. Ice thickens day by day. The sun traces its low arc across the sky without hurry. This slowness invites stillness. There's less pressure to do, to act, to hurry. Winter seems to say that it's acceptable to rest, to be quiet, to move slowly. The natural world has slowed down, and we can slow down with it without feeling like we're missing something. In this slower pace, there's space for contemplation, for noticing small details, for simply being present without agenda. When you're wrapped warm against the cold on a quiet winter evening, watching snow fall or stars appear in a darkening sky, you're experiencing something that connects you to every winter in the history of the world. The same physics that creates today's snow created snow 1,000 years ago and will create snow 1,000 years hence. The same cold that stills the world tonight has stilled it countless times before. You're part of an eternal pattern, a cycle that transcends individual human lives and links you to the deep rhythms of Earth's motion through space. There's comfort in this continuity. Winter always comes and winter always goes. In its arrival, there's a letting go, a release from the busyness of warmer months. In its presence, there's stillness and clarity. And in its eventual departure, there's the promise of renewal. But for now, For these quiet winter hours, there's just the gentle physics of cold and stillness, creating conditions where rest comes naturally and peace settles over everything like new snow. As we've wandered through winter's quiet wonders together, exploring the secret architecture of snowflakes, the profound dormancy of hibernating animals, the celestial dance of auroras, the gentle tilt of our planet bringing the solstice, the serene freezing of lakes, the great journeys of migrating birds, the patient dreams of dormant trees, and the peaceful physics of winter stillness. Perhaps you felt yourself settling deeper into comfort, your thoughts becoming slower and softer, your breathing falling into an easy rhythm. Each of these topics reveals something fundamental about our world. The complexity hidden in simple things, the elegant solutions life has found to challenging problems, the beautiful patterns that emerge from basic physical laws, the deep interconnection between all things, from the tilt of Earth's axis to the behavior of water molecules to the strategies of survival employed by countless species. Winter invites rest, and you've accepted that invitation. Your mind has wandered through snowy landscapes and starlit skies, accompanied by migrating birds and sleeping bears. Witness the patient waiting of frozen lakes and dormant trees. Now it's your turn to rest, to let go of the day's concerns, to drift into the peaceful darkness of sleep where your own restoration and renewal can happen. If you've enjoyed this journey through winter's relaxing science, please consider liking this video and subscribing to Deep Science Sleep for more calming explorations of the natural world. Let the quiet facts of winter carry you gently into dreams, and may you sleep as peacefully as the frozen world outside your window.